Okay, this video is about energy in chemical reactions and also about solubility of compounds in chemical reactions. So exothermic reactions are those that release heat energy to the environment over the course of the reaction. They get really hot. They make their surroundings hot. So a beaker that an exothermic reaction is in will feel hot. If you put your hand next to it, that will get hot. So they're releasing energy to the environment that is surrounding the system. So what we call the surroundings. They're releasing energy to their surroundings. The temperature of those surroundings increase. So if you put a thermometer in, you'll see the temperature go up. We can write that energy that's being released as a product. So we'll have reactants go to products plus energy is actually a product then of the chemical reaction. So think exothermic is on the outside, like an animal with an exoskeleton has that skeleton on the outside. Think of like a crab or a turtle and how they have this shell on the outside, whereas we humans have an endoskeleton on the inside. Endothermic reactions absorb energy. They take energy in, so then they feel really cold. The temperature of the surroundings really decreases when there's an endothermic change going on. So the temperature on a thermometer will go down as the surroundings get energy taken from them that the reaction takes in. If you hold a beaker with an endothermic change, it's going to feel cold to you because your heat energy is being taken away from you and it's going into the reaction. Because energy is a reactant, it's taking the energy in. So it's reactants plus energy goes to products, and energy is acting as a reactant in an endothermic reaction. Okay, what do we need to know about the solubility of ionic compounds and about precipitation reactions? Well, soluble compounds are those compounds that readily dissolve in water to form an aqueous solution. So what's an example? How about we take NaCl or table salt? We've all seen table salt in our everyday lives. It's a solid, and we put it in water to dissolve it, and we end up with its component ions. We end up with Na plus aqueous, and we end up with Cl minus ions that are aqueous. So we end up with the individual ions being formed, and we end up with those separate Na plus and Cl ions. They're hydrated or solvated, or each ion is really surrounded by water. Insoluble compounds are those that just will not dissolve in water. A common example is silver chloride is this classic white precipitate. If you put that in water, it will not break up or dissolve in ions. You will just still have silver chloride solid precipitate. That's just it. It won't break apart into its component ion. So let's talk about the solubility of some common ions, some common ionic compounds rather. So the soluble ionic compounds contain group 1A metals. So think lithium, sodium, potassium, and also the ammonium ion. The acetate ion, C2H3O2- is always soluble. The nitrate ion, NO3- is always soluble, and so is the chlorate ion, ClO3-. Exceptions to that solubility rule, there really are none, right? So these group 1A metals, ammonium, acetate, nitrate, and chlorate are always soluble with no exceptions. How about the halogens, or those halide ions, chloride, bromide, and iodide? Those are usually soluble, and the exception is compounds that contain halogens that have the silver, mercury, or lead cations. So Ag+, Hg2, or Pb2+. So silver, mercury, or lead, if they're with the halogens, are solids. But all the other halides, all the other halogen-containing compounds are soluble. Sulfate ions are often soluble, except if they contain silver, mercury, lead, barium, calcium, or strontium. Now, which ones are typically insoluble? Those that contain carbonate or phosphate, CO3 2- or PO4 3-. Those are usually insoluble. Exceptions are carbonates or phosphates that contain group 1A metal cations, lithium, sodium, or potassium, or ammonium, because we know those are always soluble. So even lithium, sodium, potassium, and ammonium, carbonate, and phosphate are always soluble. Okay, some other insoluble compounds are most hydroxides and most sulfides. So hydroxides and sulfides are also usually insoluble. What are some common exceptions? Again, the group 1A metal cations, because they always have to be soluble. Another exception is ammonium with hydroxide or sulfide has to be soluble. And then the barium and calciums with hydroxide or sulfide is slightly soluble. So those are kind of in between. If we have barium hydroxide, we have calcium sulfide, for example, those are going to be slightly soluble. So why are we learning these solubility rules? Why are they important? Well, they are important for what we call precipitation reactions. In a precipitation reaction, dissolved substances, so aqueous ones, react to form one or more precipitates, or what I would call solid precipitates, right? They react to form new solid products. So here's an example. NaCl, well, Na is a group 1 metal cation, always soluble, so it's soluble, or AQ. Reacts with AgNO3. Okay, nitrates, always soluble, so that will be AQ. So we've got these two substances that are dissolved in water. They react to form AgCl. Well, halogens like chlorine are usually soluble, but an exception is silver, and that makes a classic solid precipitate. And then we've got, it also makes NaNO3, well, nitrates, sodium nitrate, for example, always soluble, or AQ. So what's the precipitate? It's this silver chloride. That's the precipitate. Sometimes after it, we write a little arrow downward to mean that that's a new solid kind of falling out of solution, that when we mix these two solutions, we get this new solid product. It's a precipitate almost in the way that snow is a precipitate. Think of it as a chemical snow globe, right? You've got a beaker, you mix two aqueous solutions, and all of a sudden the snow in the snow globe starts to form, and it really precipitates that new solid product. Okay, so here's some more practice. Identify the aqueous compounds and the precipitate in the following reaction. So we use our rules from our prior slide. We have K2SO4, potassium sulfate. Okay, well, what do we know about potassium sulfate? Group 1A metals like potassium, K is a plus, 1A metal, are always soluble, AQ. Barium nitrate, nitrates are always soluble, AQ. Reacts to form 2KNO3, potassium nitrate. Well, the 1As and the nitrates are always soluble. This one's double soluble. And barium sulfate. We should check on barium sulfate. Sulfate ions are usually soluble, but barium is on the list of exceptions in that it is not soluble. That's your new solid precipitate. That's going to precipitate out of solution, just like snow in a little snow globe, kind of raining down this little precipitate. Just like precipitation in weather means rain or snow. This is kind of like your solid chemical snow, if you will, or precipitate. Okay, let's try one on our own. Write a balanced equation for the following reaction and identify the precipitate. So we've got lithium bromide. So lithium is a group 1 metal, it's plus. Bromine is a halogen, it's minus. We've got silver acetate, Ag is a plus. Acetate is our polyatomic ion, C2H3O2, and it's minus. So we've got plus, minus, plus, minus. Everything is balanced here, so we can start writing it out. Okay, so we've got lithium bromide. The 1As are always soluble, AQ. We've got silver acetate. The acetate ions are always soluble. Okay. And then we need to figure out what products it makes. I like to do something that folks sometimes call the rainbow method. It's just a way of figuring out what your products are. You're going to take your first cation, lithium, and then you're going to match it up with your second anion, the acetate, C2H3O2. Okay, so you're going to put those together to make Li plus and C2H3O2 minus as your product. Li is a plus, C2H3O2 is a minus, so that all works out. And then the second half of your rainbow is going to be to take the Ag cation and go backwards and match it up with bromine. And so that's what makes it kind of look like a rainbow, is that we had, first put together our green ions, and then we put together our blue ions, just as a way to kind of remember how to put them together. So what were our blue ions? Those were Ag's a plus, and Br is a minus. So we're always writing the cation first. So lithium went first in the reactant side, it goes first in the product. Silver goes first, silver goes first. So those cations are listed first. Now, we need to think about solubility. I kind of missed that here, so I've got to write it back on here. We said that acetates were always soluble, so this one was AQ. Group 1s like lithium and acetate, those are both always soluble or AQ. What about this silver bromide? Well, the halogens like bromine are soluble, but silver is an exception. So that's going to be your new solid. That one's going to precipitate out of solution. So silver bromide is your new solid precipitate in this reaction. So when we say identify the precipitate, that would be AgBr. Solid is our, is our precipitate here. Okay, we have one more reaction to try here. It says write a balanced equation for the following reaction and identify the precipitates. We've got calcium chloride. Well, calcium is a group 2A metal, so it's 2 plus. Chloride is a halogen, -1, so we're going to need 2 of the chlorines to balance out calcium's 2 plus charge. And then we've got ammonium sulfate. Okay, ammonium is NH4 plus. Sulfate, though, is SO4 2 minus, so we're going to need 2 of those ammonium ions to balance out sulfate's 2 negative charge. So let's start writing this out. We need a line for balancing. It says to balance this, and we're going to have calcium chloride, CaCl2. Now, those, we could ask ourselves, okay, let's look at our rules. Is calcium chloride soluble or not? The halogens like chlorine are generally soluble. Exceptions, though, are silver, mercury, and lead, but we don't have silver, mercury, or lead, so let's write AQ plus, we're going to write ammonium, H4, and there are 2 of those, and a sulfate. Okay, reacts to form. Well, let's sort of use our rainbow method here where we say calcium is going to get together with sulfate. When they do, calcium's a 2 plus and sulfate a 2 minus. So they're just fine being calcium sulfate. And then we'll just put ammonium with chloride. NH4 plus and Cl minus. Oh, that's already balanced too. That's just NH4 and Cl, or ammonium chloride. Okay, well, sometimes this is called double replacement or double displacement because we've got two compounds and they're both going to switch ion partners. So calcium is now with sulfate, ammonium is now with chloride. This is kind of a double switcheroo or double displacement, or sometimes people say double replacement. Okay, let's try to balance this. Let's make an atom list. We're going to have calcium, we're going to have chlorine. Let's keep ammonium together as a polyatomic ion, and let's keep sulfate together as a polyatomic ion. And then let's do some element polyatomic ion counts. We've got 1 calcium on the reactant side, 2 chlorines, 2 ammoniums, 1 sulfate. On the product side, 1 calcium, 1 sulfate, 1 ammonium, and 1 chloride. Okay, we really need to double our chlorine and ammonia counts here. So 2 chlorines we'll get by doubling ammonium chlorides. We'll double that for 2 chlorines and 2 ammonias, and that's all we need for balancing. We can leave these blank or we can put in ones. And then let's go back and consider our solubility rules. We need to consider first ammonium sulfate. Ammonium ions are always soluble, AQ. So we go to the product side. Well, ammonium ions always soluble, AQ. What about calcium sulfate? Sulfate ions are typically soluble, but calcium is an exception. So that would be your new solid precipitate. So when we're asked to identify the precipitate, that's our calcium sulfate. That's our new solid precipitate. So we want to be able to write out these double displacement reactions. We can use the rainbow method to predict products, then we can balance them, and we can use our solubility rules to predict what the new solid precipitate is that's been formed.